analysis of digital modulation schemes. Last time we talked about PSK. Let me write the general form. The modulated signal, PSK of t, is a cosine 2 pi SCT plus 2 pi over capital M times little m, where m goes from 0, 1, 2, all the way to n minus 1. That gave us a constellation of symbols which all resided on the same unit circle. Remember, they were all on the same unit circle. Let's say in the case of A PSK, those were the points of your constellation. And this 2 pi over m was an angular separation between them, and then there's capital M symbols, where depending on how large m is, you can modulate certain number of bits on a symbol. We did this last time. Let me just remind you as what was the final result. We went through some basic math and discovered that this is a cosine 2 pi m over m times essentially, let me just make sure that I keep the same notation. Okay, so there was also, okay, so g t of t cosine 2 pi SCT, and then times a sine 2 pi m over m times minus gt of t times sine 2 pi SCT. This is what we said was the, if you do some math, what is missing here is a times gt of t, the pulse that you're signaling with. Now you can see that this is essentially two-dimensional modulation scheme, where this a cosine 2 pi m over capital M is modulating our basis vector psi 1 of t, right? Actually, this whole thing gt of t times cosine we define as square root of energy times psi 1 of t. And then in the lower branch, I had a times sine 2 pi m over capital M times square root of energy times psi 2. And these are the two vectors that I have here as well, psi 1 and psi 2. So this kind of reveals the two-dimensional nature of the PSK, where what you actually do is combine a little bit of cosine, a little bit of sine, and then they together result in an appropriate phase shift. This equation here also points to a direct way how I can generate PSK signal. The way how we do that is very simple. We have bit stream coming in. So these are your zeros and ones. We have something that we call S to P, serial to parallel, which essentially a block that calculates these two, a cosine and a sine. Depending on which symbol I select, it will calculate for that symbol what is the value for what goes in the upper branch and what is the value that goes in the lower branch. So upstairs, then I have my gt of t that will transition from digital world to analog, and then here I would multiply by cosine 2 pi SCT. This comes in as a plus sign, and then here I have the same filter, gt of t times sine, or minus, or let's put it minus sine of 2 pi SCT, and then I'm going to sum this 2, and this becomes my u PSK of t. So that's the direct modulation of how you would actually generate the PSK signal. What I'm placing upstairs is this a cosine 2 pi m over m. And what is happening downstairs is a sine 2 pi m over m. So now you should kind of understand how this scheme works. Let's say I use this, let's just do it this way. So example, let's look at our bit stream that looks somewhat like this. This is what is coming into the modulator here. Let's label these guys. This is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? So these are our 8 symbols here and the 3-bit combinations that I have for each one of these symbols. Let's say this is my bit stream, so I need to, these two will be grouped into a symbol. Looking into this chart here, this is symbol 0, 1, 2, so it's going to be, let's label this as U0, U1, U2. So I need to be transmitting U2, right? So this thing here results in U2. So if I look at U2, what is that? This is 0 times psi 1 plus 1 times psi 2, right? So therefore, what I place on the upper branch is going to be, I'm going to select actually m equal to 2, and then a cosine m pi over 2 becomes 0, and a sine m pi over 2 becomes 1. Is that cannot be right? So let's see. What I have here, this is my, so if I select this symbol, this is 0 times cosine and 1 times sine. But then m, oh yeah, because it's u, this is m equal 0. Okay, so this is m equal 1, m equal 2. Oh, what I'm missing here is 2 pi. Okay, 2 pi over m. So it's 2 pi m over m, right? So when m is equal to a, so let's just do it again. So it's a cosine 2 pi times 2 over 8, which is cosine over pi over 2, which is 0. And downstairs I have 2 pi m over m, but sine. So I have a cosine 2 pi, no, not cosine, sine, 2 pi times 2 over 8, which is just a, right? So what goes on the upper branch is 0, what goes on the lower branch is a. And then what happens after here is I multiply with this gt of t and then with appropriate sign. Right? So what happens here is my ut is k of t becomes a gt of t times sine 2 pi times sine just a, right? gt times minus sine 2 pi SCP. That's the angle. Or I can say that this is equal to a gt of t times cosine 2 pi FCT plus pi over 2. Okay, so that's how you modulate. And then the next symbol comes in. Here's this 0, 1, 1. So that's this guy. So here you're going to pick, you're going to calculate what your A is going to be, what needs to be here as the projection on this axis, and you're going to calculate what goes here, and then you're going to feed this, and whatever comes here, it will be a properly modulated signal. So you see how the PSK signal looks like in a time domain. You can think of this as your signaling intervals, where you modulate 3 bits at a time. And here is, for example, one angle, and then you get to this boundary, and at this boundary the angle may change. Right? And at this boundary the angle changes again, and so on. So the receiver sees this essentially cosine waveform that always has the same energy, same power, right? Because the magnitude is always the same. But at the boundaries of your symbol interval, this phase here will change. So what I'm observing at the receiver, I'm just observing these phase changes. As the phase change, depending on how much the phase change or where they go to, then I can decide which one out of these 3-bit combinations will send. Right? So you're sending 3 bits at a time here. You know, you detect what the phase is. You map that phase on this diagram, and you recover your 3 bits. Okay. Let's calculate the Euclidean distance between PSK signals. PSK symbols. Let's look at 2 symbols, Sm, which is square root of energy cosine 2 pi over capital N times n, and the second coordinate is sine of 2 pi over capital N times n. And the second symbol, Sn, which is square root of energy cosine 2 pi over m times n, and then sine 2 pi over m times n. So I have 2 vectors, 2 symbols from this constellation here. And the question is, what is the distance between them? Euclidean distance we define as the norm of the difference, actually. Norm of the difference between these two symbols. So when we derive this kind of representation, we show that you can calculate this distance either in time domain or in a vector domain. So I'm just going to do this as a straightforward calculation in a vector domain. So I'm looking at the square root of energy, norm of the vector, that is cosine 2 pi over m times m minus cosine of 2 pi m n. So that's the first coordinate. And the second one is sine 2 pi over m times little m minus sine of 2 pi capital M times n. Looking at the norm of this vector. What is it that we're looking for? Let's say this is our constellation in case of the PSK. And this is Sm, and this is some Sn. Right, so these are the 2 vectors. The difference between these 2 vectors is this, right? This vector here is Sm minus Sn. And what we're looking is the norm of this distance, how far these 2 vectors are, how separated they are in a constellation domain. This is psi 1 and psi 2. So how do we calculate the norm of the vector? Well, it's a square root of the dot product of the vector with itself. So what I need to do is to take the squares of these 2 coordinates and then add them together and take the square root, right? So this becomes cosine 2 pi over m times m minus cosine 2 pi over m times n. So that's my first coordinate, so let me square this one. Plus the second coordinate is sine 2 pi over m and minus sine of 2 pi over capital N times n, and then that squared, and then I have to take the square root of the sum of the squares, right? That's the length of this vector here. Now, I know there, you see right away when I start squaring there's going to be a lot of terms, so let's pay close attention and so we can minimize some of the writing, right? Look at here, from the first one you have cosine squared, do you see that? And then from the second one you have sine squared. When you add the two, you get 1. So I have 1, 1, right? From the first one I have cosine squared again, 2 pi m over times n. From the second one I have the same thing. That's again 1, so I have 2, right? 2 ones, right? So this is equal to 2. Now from here I have minus 2 this times this, and from here I have minus 2 times this. So I have minus 2 cosine 2 pi and capital M times M cosine 2 pi capital M times N minus, actually plus, sine 2 pi capital M times M times sine 2 pi over capital M times N. And then I have to close the bracket and take the square root. Now, this thing here in parentheses we recognize. What is this? It's the cosine of the difference, right? Cosine alpha minus cosine beta is cosine alpha cosine beta plus sine alpha sine beta. So this is cosine of the difference. So I simplify this as 2, 1 minus cosine 2 pi over m, m minus n, right? And there are a lot of parentheses here on top. But I can take this couple of steps more. 1 minus cosine is 2 sine squared over half of an n, right? So this becomes 2 times 2, 4 times sine squared of pi m minus n over m. Take the square root of that. And then I get a really nice, this is dmn, the distance between the two symbols, m and n. And I get a really nice formula, dmn is 2 absolute values of sine of pi m minus n over n. Right. So that's the Euclidean distance between two symbols of PSK constellation. Of the highest importance to us is really distance between adjacent symbols, right? Why is that of the highest importance to us? Because remember, at some point we're going to introduce the noise, and what noise is going to do is going to try to make this symbol look like some other symbol, right? So that it confuses us and makes us erroneously detect the symbol. That's the most likely to be the occurrence among the symbols that are adjacent to each other, right? It is going to be relatively hard to turn this symbol into this one. You need to do quite a bit of the distortion. You're going to turn this symbol into its adjacent ones. So of the greatest interest to us is when n minus n is equal to 1. And let me do some calculation. You can see that there are two things here, that this distance depends on the difference between n minus n and on the capital N. How large is the number of symbols in our constellation? I've just noticed that I made a mistake. Can you see where I made a mistake here? Nobody? No? There's something missing.
Yeah.
Plus? Where's plus? Energy, right? Energy. Everything scales up with an energy. So I apologize for that. So the end result here is going to have this times the square root of energy. Energy is what, kind of blows up this circle or shrinks it down, right? The energy is the radius of this circle. The way how you should see this, or how I frequently picture this myself, is when you're transmitting, your circle is this big, right? But then as it travels, it kind of shrinks as well, right? Because your energy dissipates, and then the receiver looks at the circle that's this big, and those symbols are now getting really close. And then once you start having noise, then you're going to start having really hard time deciding which one of these symbols is going to make sense. All right, so let's take a look at what does this distance end up being for different m's. So when m is equal to 2, then you have the distance is square root of energy, and then you have 2 times sine pi over 2. Sine pi over 2 is equal to 1, so you have 2 times 1, which is 2. So let me just write this as 2 times square root of energy. When m is equal to 4, distance is square root of 2 times square root of energy, which is 1.414 square root of energy. When you substitute m equal 8, the distance becomes 2 times sine pi over 8. You can see here sine pi over 8 times 2. So this is 0.7654 times square root of energy. And m is equal to 16, gives you 0.3902 square root of energy. What is it that you notice? You notice that for the same energy, as you start putting more and more symbols, the distance between them becomes smaller and smaller, right? And that makes sense, right? Look at our drawing here. I mean, if I keep the energy constant, which means I keep the radius of the circle constant, and somebody says, okay, m is equal to 4, then I put the 4 points, and they're separated. They're separated 1 over square root of 2, not 1 over square root of 2 times the square root of energy. But if I put 8 points, then I'm shrinking the distance between them. And the more points I put, the smaller the distance between adjacent points is going to become for a given energy. Now let me ask you this. Let's assume that this is kind of going into the future, but I want to test your understanding at this point. If you start putting more and more symbols, and you keep the energy constant, look at it now from the receiver standpoint. Is the receiver more likely to make error or less likely if you have more symbols?
Less.
Less likely? More likely, right? Because why? Because they're closer to one another. Look at it from the receiver standpoint. Let's say I look in 2 cases. The energy is constant, right? So this is the first case where you have just 4 symbols, right? Now think about this shrinking, right? So receiver sees ever smaller and smaller energy. So they're coming closer and closer, but they're still separated, right? Now let's put 16, right? So you start, so I'm doing 16 to be drastic, right? So let's say these are your first 4, then these are the next 4. So then these are additional 8, right? Look at these symbols now, right? So now, shrink this as you keep going, they become really, really close. And even the smallest noise will turn this one into this one, and you'll make, to compound the problem, how many bits per symbol do I have here? 2, right? So if I make an error here, I'm going to lose 2 bits. How many bits per symbol I have here? So if I have 16 levels, I'm packing 4 bits on every one of the symbols. So if I make erroneous detection of the symbols, potentially I can lose 4 bits. We have some ways of coding that in a smart way, but you can see that that as you keep on increasing the number of constellation symbols, to preserve the same probability of error, what is it that I need to do? Or to preserve the same distance between them? I need to pump this circle, right? So if I put more points, the circle needs to be bigger, right? so my energy needs to grow. And there's a trade-off that you should start to see between power, data rate, symbol rate. All of these things are kind of intermingled between each other. Okay, let me just put some notes, and then we'll look at slightly different digital modulations. The first note is if energy is kept constant, the distance decreases as m increases. Right? So you can see that from the drawing I have. The more energy is the size of the circle, and the number of symbols dictates how many points on the circle you have. So the more points you have, the distance between them is going to be small. If the distance is to be kept the same, needs to be remain constant. The energy needs to increase as a function of n. Right? And why is this important? Because remember, the distance, we're going to ultimately tie that up to the bit error rate with probability of making an error. The third one is for larger n, there are more bits per symbol. That's just an obvious observation, right? That we're packing more bits. The fourth observation that we make is for more bits per symbol, and for a given bit rate, the symbol rate decreases. Let me give an example here to explain what is happening. Let's say we're working with voice. What is the sampling rate for voice? How frequently do we sample voice? What's the band? What is the voice band? Telephone voice. 4 kilohertz, right? So it's 2 times the bandwidth, our sampling rate. So it's going to be 8 kilohertz, right? 8 kilosamples a second, 8,000 samples a second. How many bits per sample do we have? Usually 8 bits per sample. So the data rate, bit rate, is 8 kilosamples per second times 8 bits per sample. And this gives me a rate of 64 kilobits per second. So this is telephone voice. Telephone voice gives us 64 kilobits per second. You should remember that. That's kind of like a known communication number. All of our landline telephony uses 64 kilobits per second of the data rate to represent the voice. Now, let's say we have this coming into PSK module. So you have your RV here, and this is a PSK with a different M. And the question is, what is the symbol rate here? If M is equal to, then how many bits per symbol we have? If n is equal to 2. We have now, in case of the binary phase shift keying, or BPSK, how many symbols in your constellation you have? By 4. N is equal to 2. So you have 2. How many bits you have? 2. So 1 bit, 1 symbol, right? If it's how does the n equal 2 constellation diagram look like? 1 symbol here, 1 symbol here, right? They are separated by 180 degrees, right? So here, bits per symbol is 1, and your symbol rate is the same as the bit rate, right? So how many symbols per second I'm going to have here? 64 kilosymbols per second. Okay? Now let's take a look at n equal 4. How many bits per symbol we have here? You have 2. So what is your symbol rate going to be? RB over 2, right? Because you're going to take 1 symbol up, 1 symbol down, and then 1 bit up, 1 bit down, and send it 2 at a time. So you're sending symbols at a rate which is 1/2 of your bit rate, right? So here your symbol rate is going to be 34 kilosymbols per second. Now for n equal 8 bits per symbol, you're encoding 3 at a time, so your symbol rate is going to be RB over 3, which is 64 over 3 kilosymbols per second. N equals 16. How many bits per symbol we have? It's going to be 4, so your symbol rate is going to be RB over 4, and this is going to be 260. And so on. So what do you notice? On one end, you have the bit rate, which is kind of always constant. It comes based on your what is it that you're actually digitizing? You're digitizing voice. So the voice has bandwidth of 8 kilohertz, 4 kilohertz, sampling rate 8 kilosamples per second. To represent it with a good enough signal to quantization noise ratio, you need 8 bits per sample. So your voice is naturally represented with 64 kilobits per second. But depending on how many levels do you choose, you have a control on how fast you signal, right? You may signal at the rate that's the same as your bit rate, but you may signal at a much slower rate, right? Depending how many bits do you pack on each individual signal. Okay? Why is this important? We're going to be looking at, do you sense why is this important? Not at this time, it's too much of a stretch, but it's going to be important for us because we will show, one of the things that we always need to show for modulation is what is its spectral footprint, how large is its spectral domain. And what you find out here is the bandwidth of your modulated signal is going to be dependent on this rate. So the lower this rate is, the narrower your signal is in the frequency domain. Right? So here we don't really have a fix. In AM we just translated our baseband signal to the carrier frequency, and we have 2W. Here you have actually, depending on how you modulate, your bandwidth at the carrier frequency may actually vary, and that's one of the important trade-offs that for digital communication allows. Go ahead. All right, so let me just put that as a comment. Bandwidth of the modulated signal depends on symbol rate. And this time, this is unsubstantiated claim. I'm just letting you know why I went through this exercise. At some point down the line, we're going to actually derive this strictly, and we will show why this is the case. Okay, so that's the first way how we can modulate using two-dimensional modulation where your basis vectors are sine and the cosine. There's an alternative one. And this one is called quadrature amplitude modulation. And this one is a more general type of the modulation. As a matter of fact, it will include the PSK as a special case, but we treat it separately because, you know, it is kind of used separately. It is either you use this or you use this, and the motivations are slightly different. Right, so two-dimensional signaling. And this was quadrature amplitude modulation, or QAM, QAM. General form of a QAM signal looks somewhat like this. U m n of t is going to be am gt of t times cosine 2 pi fct plus theta n, right? So you can see that this signal is modulated in two domains. In the case of the PSK, we messed only with this theta here. We had different angles, you know, as a function of whatever comes in. Here we have amplitude modulation, and phase modulation. Working in, you know, in parallel. So we change the magnitude of the symbol as the symbols are changed, and we change their phase. We're gonna say that AM takes one of m possible values. Right? And theta n takes one of n possible values. So the number of symbols is going to be n times n. Right? So you can have any combination of all these symbols. Now let me first demonstrate that this is indeed two-dimensional modulation, and this will also teach us how we construct it and how we build a modulator that can actually make the signal that looks like this. So consider this. U m n of t can be written as am gt of t times cosine 2 pi fct cosine of theta n. And then let me actually do it this way. Minus sine of 2 pi fct times sine of theta. What did I do? Nothing smart. I just realized that this is the sum of the two angles. I'm writing that as the sum of the two angles. But then I can look this real hard, and I can say, well, look, this I can rewrite as an cosine of theta n times gt of t cosine 2 pi fct, and then an sine of theta n times minus gt of t sine of 2 pi fct. Okay? And then I realize, oh, these two things here are nothing but my basis vectors, right? This one is square root of energy times sine 1. This one is square root of energy times sine 2. So I see umn of t as am cosine theta n times square root of energy times sine 1 of t, and plus AM sine of theta n times square root of energy times sine 2 of t, where sine of 1 of t is my gt times cosine, and then this other one is the square root of energy times. This one here is the sine, right? So I have two carriers in quadrature, which I'm using as a basis vectors. So equivalent vector representation is UMN is going to be the square root of energy, and then AM cosine of theta n and AN sine of theta n. In general case, I'm not restricting what these AMs and theta n's can be. In case of PSK, I had to be on unit circle. Here, I don't have to be anywhere. So I can write this as just square root of energy, AM along the cosine and AM along the sine, right? So I just pick two coordinates, pick a point in the constellation plane, and that becomes one of the symbols that I'm using. Now let's draw some examples. Let's look at the first one, and let's pick two values along this side 1, and this is side 2. Let's pick two values on this axis, and then pick 4 points, right? So what is this? Well, somebody can say QPSK, and they would be right, but this is also 4 quant, right? Where you have, pick these 4 points, right? You have two along the values for AMC and two values for AMS, and they give you 4 possible combinations. So that would be one example. Let's look at another example, maybe better. Let's put 4 points this way, 4 points this way, and now look at all possible combinations. So, I'm sorry, this one doesn't fall. All right, so this is side 1, side 2. How many points do I have here? Well, I have 4 possibilities this way, 4 possibilities this way, so I have 16 points. This one is called 16 quant. Right? If I pick 8 points this way and 8 points this way, how many do I generate? 64, right? So 64 quant. And this can go a lot of points, right? So you can have a lot of points in this plane here. What you find out here is where's the major difference between this and the phase shift key. Here, as you grow the number of points, they are not getting close as fast as in the case of the PSK. In the PSK, they have to be all in a unit circle, right? So as you keep on putting a lot of points, they all kind of become dense. The inside area of the circle is unused completely. Here, you use much more efficiently this plane, but so these, for example, if I try to put 16 points on a circle, they would be very close. But here, they're still separated apart, right? The price you pay is that in the case of the PSK, all the symbols have the same power, same energy, right? So from the standpoint of linearity of your circuits and the practical implementation, that's a good thing. You have your constant power that goes through all of your amplifiers. Here, the symbols are separated, but they all have different energies, right? The energy of this one is the highest. Then this one, this one, this one, this one, this one, this one, and this one, they have the same energy. and then these 4 here have the smallest energy, right? So you have, these guys have the smallest, then these 4 have the largest, right? How do I somehow designate them? And then these, the ones that are left, have the in between the energy. So you have signals of different energies. So that means that you signal, your energy of the signal or power of your signal are going to change. So that means you need to have more linear circuits than in the case of phase shift key. How do I generate quantum signal? Here's the block diagram. You have bit stream coming in. There is our S to P device. S to P device now says, okay, whatever combination of bits I have, let's say I'm using a 16 quant, so I take 4 bits at a time. I identify these 4 bits with one of the symbols in this constellation here, and then I calculate the value. For example, let's say I identify this one. So here is your AMC, and here is your AMS, right? You're going to have 2 coordinates. You're going to have coordinate on the psi 1, and then a coordinate on the psi 2. So it will calculate these 2. It will put AMC on a top branch. It will put AMS on a lower branch, then it goes into GT, and then into your cosine 2 pi FCT, and here is the same GT of T times minus sine of 2 pi FCT. And these 2 guys, and here comes your U quantum T. So this is your modulated signal. Now let me ask you this. How is this different than QPSK? Not QPSK, it's PSK. How is this different than phase shift key? The answer is it's not. Right? It's not. It's the same modulator. Right? Same kind of modulation, right? The PSK is a special case of quantum, where instead of picking points on a rectangular grid, you pick them all to be on the circle. But every point that you pick will have a coordinate. The x value of that coordinate will be done here. The y value of the coordinate will be done here. In practical circuitry, this is the demarcation point between the 2 worlds. On the left, it's all done in digital domain. Alright, so that means that what I'm drawing here is just some numbers, some software running this, right, in your phone, or software running in your modem, right? It's taking the bits, it's doing calculation, and it's determining what these numbers are. And then these numbers are here, translated into proper signals in a time domain. Whatever, let's say this one is this big and this one is this big, right? This is GT, and then it gets modulated and sent through the system. Many systems actually try to push this boundary and take it all the way up to here. Now you can say, well, how is this possible? Well, you can digitize sample cosines, right? And you multiply everything, and then you actually end up with a sampled version of this signal that you then pass to digital to analog converter. It generates the form, and then you translate that form to whatever is the operating frequency. There's a great benefit in this because you can do a lot of it in pure numbers. And what happens is when you do it in digital domain, you're absolutely in control of your accuracy. There's no aging of the components. You know, if the software works today, it works tomorrow, it works 10 years from today in the same way. Right? It's not going to age or change its characteristics or go under corrosion or whatever is the things that we experience with the real hardware. But you know, from the theoretical standpoint, we think of this part to the left as digital, and this part here to the right is analog, where you transition from digital signal processing here into analog domain, where you're going to send everything to the from the transmitter towards the receiver. Any questions here? So these are the two. We kind of covered three modulation schemes so far. We covered one-dimensional pulse amplitude modulation. And that one we said you can signal at baseband and you can signal at bandpass. But most of the time we use that one when we signal at the baseband, right? You don't have modulation up or down. You're just forming bits and you're sending them to the other side. Right? The second types of the modulation we cover with two-dimensional modulation, when you signal along two basis vectors. One, we discovered, you know, although theoretically this is pretty cool and you can come up with a lot of interesting theoretical results. In practice, we have two naturally given to us basis vectors. One is cosine and the other one is sine. And we can modulate them in a two similar but a little bit different way. One is we modulate them in using just a phase, which means all our constellation points are on a circle. They have the same energy. And the second one is we modulate them both in phase and magnitude, in which case our constellation points are distributed throughout the signal space, and we end up with a quadrature amplitude modulation. These two are very similar. They actually use the same modulator to create the signals. The difference is just this element here calculates different values that it puts on what we call here I and Q branches. This is usually called I, and this one is usually called Q. And this is I and Q balance modulator. You can actually buy a circuit that is just this, and that you actually feed with AMC or AMS, whatever you want it to be. So this is how we modulate. Let's look at the second thing, and this is how do we demodulate. Let's say we have formed this signal. It travels through our AWGN channel. It gets corrupted by noise. And now the question is, how does the receiver detect what it has been received? What is the incoming signal? So let's discuss demodulation. Actually, reception, and then we'll look at what that means in digital. Okay, so the reception of digitally modulated signal in AWG. So I have my transmitter here. This is the essentially block diagram, and it makes some signal SM of t that is any one of those signals that we talked about. It's either your pulse amplitude modulation or PSK or quantum. The signal travels through AWGN, and it is corrupted with noise here. And I'm going to call this signal R of t as my reception signal. So in here, M is going to be equal 1, 2, all the way to M. And this R of t is received signal. We before we go into great detail about how all of this works, let me point out the most significant difference between amplitude and digital modulation. Why is digital modulation so much better fundamentally? In the analog world, what we try to do with the receiver is recover the message signal itself, right? So every impairment that was captured by the channel would actually show somehow in your message signal. It will be either rejected by the processing gain or whatever the receiver does. But if the noise was co-channel or co-spectrum with your signal, it would impact the signal, right? Because the receiver strives to reconstruct the signal as it was sent, right? If I send you, I don't know, sinusoidal, I better see a sinusoidal and yeah. When it comes to digital receiver, the task of the receiver is substantially different. Here's what the receiver knows. The receiver sits here and it knows I cannot receive anything, right? I have to receive one of distinct m possibilities, right? It cannot be any signal. It can be Sm of t, where the number of these m's is finite. Right? Let's say I'm receiving a QPSK modulated signal. I have to receive a sinusoidal, and it has to have a phase either pi over 4, 3 pi over 4, minus 3 pi over 4, or minus pi over 4. Just these 4 possibilities. So my task is not necessarily to reconstruct the sinusoidals. I couldn't care less about the actual waveform. What I need to do is look at what is coming in and decide what has been sent. And once I make the decision, if I make the correct decision, I can actually discard the signal that I have received and regenerate it without any noise, right? Because I know exactly what has been sent, right? So let me actually give this even simplify. Let's say somebody is signaling with the binary pulse amplitude modulation. So what does the receiver know? It's either 1 or it's -1. There is no other possibilities. So if it receives something like this, what it will say? What has been sent? 1, right? If it receives something like this, what has been sent?
1.
Right? If it receives something that looks like this, what has been sent? 1. How do you know? Right? Because the area under the is positive, right? So you see how distorted this is from the original. It's very distorted. The signal-to-noise ratio is very poor. But your task is much easier. You kind of squint, you look at it. Oh, it has to be 1. Even though it's distorted, I can see that it's mostly positive, and therefore it has to be 1, right? So that's why, in generally speaking, digital modulation is way more robust, because the receiver task, your transmitter first, it doesn't have much of a control. It has to convey all the information through a limited number of waveforms, limited number of symbols, and then receiver knows what is to expect. It expects one of m possible symbols, and decision here is don't really reconstruct the symbol. Try to decide what has been sent. And once you make a decision, if your decision is correct, I can translate this into a pure symbol that has been sent, and essentially have infinite processing gain, right? Because I'm going from a signal-to-noise ratio that is something to essentially signal-to-noise ratio that's infinite, right? So my receiver is giving me, as long as you make the decision correctly, you're gonna remove all the noise. Now the question here is, if I receive something like this, what has been sent? You can just guess, right? And then sometimes you're going to guess correctly, sometimes you're going to guess incorrectly, and in this case you're going to make an error. So when it comes to characterizing all of this, we're going to talk in terms of probability of making a decision error. Okay, so that's kind of introductory. So this is where we're going. Let me spell out what some of these things are here. Sm of t is one of possible m waveforms. M waveforms. In most systems, m is some power 2 to the k. The reason is practical because we usually start from binary data and then we are mapping certain number of bits to a single symbol. N of t in this expression here is a Gaussian noise with zero mean and sigma squared as it's so this is a Gaussian. It's Gaussian in amplitude domain. It's white in a frequency domain, right? So its power is really infinite, but that's why we're always going to have some sort of filtering here before we try to recognize any one of the symbols to reject most of the noise that are not co-channeled with the signal. Now, here we're going to be defining something that I'm going to call capital T, which is going to be symbol period. In this course, we're going to look at one symbol at a time, right? That's the simplest way of how the receiver works. It receives one symbol and immediately makes the decision on what has been sent, right? There are alternative ways where you can receive, let's say, 50 symbols or 10 symbols and then try to decide jointly what is the 10 symbols that I'm receiving. Let me give you just an example and then so that you can see the difference. Let's say somebody is sending, you're now a receiver, I'm sending you an English text. How many symbols do I have in my constellation? 26, right? In English, nobody's here. Oh, no. So 26. So I'm sending you one of 26 possible letters. You as the receiver, you're trying to decide which one out of 26 letters I'm sending. Is it A, B, C, and so on. So that's that's what we are going to be concentrating now in this course. But how can it be different? Well, I'm sending you a text, so you may wait, and then you actually try to recognize words as a whole. So therefore, you're going to be having less of errors, because sometimes, even though some letters in some words may be erroneous, when you look at a word, you may recognize the word as a whole. And that's what error control coding does to us. So it introduces redundancy in your stream, so that when you look at combination of symbols, some of them are more probable than the other ones. This is a little bit more advanced topic. We covered it in digital communication. For right now, we're going to be focusing on the simplest possible way. And this is I'm receiving one symbol at a time, and I need to decide which symbol that is. You know, outside of the word, right? Just one symbol at a time. Okay. So, so the receiver performs two tasks. Two tasks. First task is demodulation. And this is essentially the inverse process than the one that happens here, right? You go from a symbol into the analog waveform. I need to go from the analog waveform into the symbol, right? So the demodulation will take R of t and make it some vector R that is going to have components Rn, R1, R2, Rn. Okay? N is the number of basis vectors. So it needs to look at this signal and say, hey, in my symbol space, where is this point? Right? So how do I do that? I'm going to take whatever comes here and decompose it along my basis vectors. So So that's the first task. The second task is detection. So here, receiver makes the decision on which one out of n possible waveforms has been sent. Okay? Before we kind of go into both of these in more detail, let's go again and look at our constellation and see what is it that is actually happening here. So here's what I'm sending. Let's say I'm signaling with QPSK. So this is at what is happening at the transmitter. Depending on what combination of bits I have, this is what I'm going to send. Right? What does the receiver see? Well, the receiver is going to receive a point, let's say here. Okay? How did this point get here? Well, the receiver actually received R of t, and then it translated this into a point in space. So this is my vector R. R has two components, R1 and R2, which are these two coordinates here that I have, and that I have in my vector there. And now that's the end of the first step. In the second step, I need to look at this as a receiver and say, which one out of these possible 4 points has actually been sent? And in this case, what is it? What is your choice? You say, well, in this case, the most probable is that this was the point that has been sent. So this is your detection step. The way how I usually explain this process, imagine, so first, let's look at this. This is your SM. What is this difference here? This is your noise. N, as it is appearing in this space, right? So the way how I usually kind of give an example here is, imagine a drunk guy throwing a dart, right? And if he's an excellent dart thrower and not drunk at all, he will be hitting this point every time. But as soon as you start introducing noise, and that's kind of drinking here, you start weaving away. So you're going to be hitting points around, right? And as long as the noise is small, your cloud is still going to be okay. You're going to be in the vicinity of the point. Every now and then you may actually hit here, right? And that receiver will be confused and make the erroneous decision. But then if the noise grows, then all of a sudden you're throwing all over the place and the receiver cannot recognize, right? So that's what we're kind of up against here. So we need to quantify this. First, we need to see what is the best way for us to perform this transition from R of t into R. And then once we know this, what is the best way for us to make the decision? And then the third step is, depending on the relationship between signal and the noise, what is the probability of the receiver making an erroneous decision? So these are the steps that we need to cover. So, demodulation. And this is the first type, which I'm going to call correlation type. Here's what we're going to do. We're going to feed this signal R of t into something that we call demodulator. And what comes out are these R's. R1, R2, all the way to Rn. How many R's I'm going to have, depending on the size of my basis set. Whether if I'm using one-dimensional modulation, then I just have one. If I'm using two-dimensional, then I'm going to have two, right? Or multi-dimensional, I may have more than one. What is this RK? RK, how do I determine what portion of R of t is along the first basis vector? What do I need to do? Take a dot product between them. I need to project my vector onto the basis vector, right? So I need to determine what is this value of this R1. And the way I do that, I take my R of t, project it of psi 1 of t. We know that this is an integral from 0 to t, R of t times psi of t dt. That's our dot product. But now you can see that I can write this as integral from 0 to t. This R of t is your Sm of t plus n of t times psi of t dt. This is integral from 0 to t, Sm of t times psi of t dt plus an integral from 0 to t n of t times psi of t dt. What is this first one? What is that? This is a projection of what? Of my symbol or my signal from the signal set onto the basis vector. I already know that this is S, M, this is K, right? K, right? Because I'm projecting everything to the K basis vector. So this is going to be SMK plus NK. So this is my coordinate of the symbol along this particular vector, and this is the noise that exists along this particular vector. In this case, if you look at it, this one here has a coordinate over here. This is SMK. And what is this difference here? This is NK. This is the noise that turned this coordinate into this R1, right? So the noise is going to have a component along the psi 1, and the noise is going to have a component along the psi 2, which resulted in offset of this point into what has actually been received. So if you look at the correlation receiver, it's actually very, very simple structure. You know, let me just draw it. So correlation receiver. So you have your R of t coming in, and then you have all of these branches, right? One branch per every side that you have. So this is side 1. You're going to, of t, you're going to integrate from 0 to t, and then you're going to sample at kt intervals. And here you're going to have Sm1 plus n1. So that's going to be the sample of the waveform along the first basis vector plus the noise that's snuck in from the first basis, along the first basis vector. This is psi 2 of t, the same story. You're going to integrate from 0 to t dt, sample that at kt, and you get Sm2 plus n2. And then the last one is going to be your psi n of t, 0 to t dt, sample at kt, and this becomes Sm n plus n. Right? So that's a very simple way how you translate. You take your input signal, you're constantly multiplying it with basis vectors, integrating over the big interval, and then you're getting these components in your signal space on basis which you need to decide what has actually been sent. Right? So that's the direct implementation of the math. It would have been very difficult for me to actually draw this and try to explain this without all of this introductory view of things through a vector space, right? Because the question is, why are you doing this? It's very difficult to explain it other than, through this understanding of how do we actually signal. We signal by combining the basis vector, and we demodulate by looking at, in your signal, what portion of each of the basis vector you have. And that goes back to my analogy, creating colors. You mix 3 colors. If I want to recognize what has been sent, I actually decompose along the colors, and I see what portion is red, what portion is green, what portion is blue. Okay, so let's stop here. I'm going to introduce a different architecture that kind of addresses one fundamental problem in this one. And we'll go from there.